Hello, and welcome to Team B's final project report. First, let's talk about question generation. We use 6 different techniques to generate questions, which can be divided into 2 different categories: techniques which use text patterns and those which use grammatical patterns. The techniques based on grammatical patterns generated many more questions. However, we found the quality of questions generated by a method is often inversely proportional to the number of questions generated. The pie chart shows the results of running our techniques on all 40 of this year's supplied articles. Our first techniques were based on text patterns. For an example of this, consider the sentence from the article. In 1872 to 79, Cunningham published the first to wrap and seal. We wrote a regex to identify sentences which started with the word in followed by a time. If a regular expression matched a sentence, we extracted the dependency parse subtree rooted at in to be the answer, and replaced in with when did to create the question. We also reconjugated in's parent verb to be infinitive, along with the other verbs connected to by a coordinating conjugation. Finally, we replace the final punctuation with a question mark. Using similar techniques, we generate lifespan, who, and where questions. We developed 2 additional techniques which generated questions based on grammatical patterns instead of simple textual patterns. One technique works by replacing noun subject of the root verb with an appropriate query word. In the sentence above, an orange draconic Pokemon Charizard is the subject of the root verb. Using Spacey's named entity recognition, we can check whether the subject is a person, political group, geopolitical entity, or none of the above. In this case, it is none of the above, and so we default to generating a what question. But this technique will generate who or what place questions if the appropriate named entities are recognized. Because Spacey's named entity recognition commonly misidentified Pokemon as locations, we included a list of all current Pokemon as a workaround. Since we only want to return n questions, we used a number of factors to rank our questions and return the n questions with the highest quality. Firstly, we looked at the length of questions. Longer questions have a higher chance of being ungrammatical because of our relatively simple patterns. Secondly, we looked at the number of clauses in the question. Questions with multiple clauses have a higher chance of being ungrammatical for the same reason. Thirdly, we used Stanford Core NLP to check whether our questions were syntactically correct or not. And lastly, we looked at the source of the question, as in how much we trusted the method that generated it. The final score for each question is a weighted sum of the factors described. With this automated question ranking method, we were able to return the n best questions we generated based on the above metrics. Here are a few examples of questions we generated and their scores. The scores are all in parentheses as follow on a scale from 0 to 1. As you can see, the highest ranked question is a score of 0.86. It is ranked highly because it was generated by a who method, which produced very good results. Additionally, it had a very short length and only one clause, and was successfully parsed by Stanford Core NLP's constituency parser. Now let's talk about answering questions. Based on the words used to pose the question, who, when, where, etc., we can classify questions based on the answers they are looking for. The pie chart shows a breakdown of the different kinds of answers and questions across 4 different sets from question-answer dataset. We can further specialize question answering techniques based on the similarities and patterns that exist within these categories. The first objective of the answering pipeline is to understand which sentence in the article pertain most to the question. We do this by finding sentences that retain the most stems, named entities, and capitalized words from the question. Some answer types can be tagged by a named entity recognition system. Those entities can be extracted from the sentences most resembling the question, provide a best guess of the entity that question was looking for. However, the NER tagging system is far from perfect, and entities are often mislabeled and not recognized at all. So we have text patterns as well, where many text patterns we found that either precede or encase the portion of the sentence we are interested in. Based on the type of question being posed and sentences pertinent to the question, we can often find answers without needing them to be tagged ahead of time. We created simple ad hoc techniques to answer questions we label as true, false, or noun phrase. They answer true, false with yes or no, what happened in date with an appropriate sentence from the article, and what is blank with the appropriate clause from appropriate sentence. For the sake of time, we'll only go over true, false answering techniques. Our true, false question answering pipeline is applied to questions containing clauses which start with the lemmas of is, did, had, can, or could. This technique answers yes only if the question in the document can be found which contains stems of all the words after the first noun chunk of the question. When none of our answering techniques work, we return to the sentence in the document that is closest to the question. The main software tool we used was Spacey. It provided a large array of natural language processing tools we found very useful. We used it over its competitors because of its object-oriented design and comprehensive documentation. Our team adopted a number of innovative techniques which we think set us apart from other teams. First, we were able to implement a variety of different techniques to generate and answer questions. We were able to use the best results from our different techniques by employing question ranking, question generation, and question categorization for question answering. Next, we use an automatic evaluation system to measure the performance of our answering techniques. In addition to reviewing manually questions for answers, we calculated the precision and recall of our answers across the entire S10 question answer dataset. Finally, we use good software development practices, tracking outstanding issues on GitHub and performing code reviews. We hope you enjoyed our project, and thank you for the class.